In part 2 of the video on torque, we're going to look at some examples for calculating torque. In this particular problem, I have a bar, and there are three forces, a 10 Newton force here, a 15 Newton, and a 20 Newton force applied to this bar, and I'm asked to calculate the torque for following set of axis of rotations. First, about a point where you've got an axis sitting right here, perpendicular to the page. Now, when you've got a two-dimensional problem like this, the torque is either going to be into the page or out of the page. And in our free body diagrams early in the semester, we drew x and y axis. What we're going to have to do now is add one more thing, the torque. Now the torque could be out of the page. If you go x into y with your right hand, your thumb will be pointing out of the page, and that's in the z direction based on what I have here. Such a coordinate system, because you use the right hand rule, is called a right-handed coordinate system. For us, rather than drawing the three dimensions with your thumb pointing out, I'm going to do this. I'm going to draw an arrow in the way I would wrap my fingers and put a plus sign. If you wrap your fingers in that way, my thumb, which is pointing out of the board, is in the direction of the positive torque, in this case the z direction. But the way I can think about it when I'm computing these torques, although I know it's out of the board or in the board, is that if I think of the bar stationary, if I pull on it with a force and it causes the bar to rotate in the direction of my arrow that has the plus sign, I will call that a positive torque. If it causes it to rotate in the opposite direction, that is, the bar in this case moves counterclockwise, which is opposite of my plus, then I will call that a negative torque. And I will just use plus and minus signs and not put the K hat or out of the board or into the board type notation. This is much like what you did in Chapter 2, where we were doing one-dimensional problems and we were saying they were either plus or minus velocities. We get away with the same reason here. Now, if you're doing three-dimensional problems like engineers or physicists do, then you'll have to deal with the more powerful methods for handling cross products. But we will not mess with them, at least in the trig-based physics course. So we'll just deal with this plus. Rotate in the direction of the arrow, it's a positive torque. If it makes the object begin rotating in the opposite direction, we would call it a negative torque. Now that's assuming it started stationary. That's what we're going to do. Now, for this one, to calculate the torques about C, notice I'll put a subscript to indicate about which axis, because torque always depends upon the axis of rotation. For this particular force, it has no moment arm. It's applied at C. Therefore, it causes no torque. Now, you could write it down like 10 newtons times 0 meters, or you could just leave it off. For this second force here, we need to calculate the moment arm. The moment arm is this distance right here. There's my little r. And that distance is 2 meters. We also need to figure out how much of the force is perpendicular to it. That is like this. Well, that's this side of this triangle here, which is 25 degrees. So I need the trig function gives me the opposite side, and that's the sine function. So it's 15 newtons times the sine 25 degrees. If I pull on it in this direction, this bar will rotate like that. That's clockwise, which is opposite of my plus. So this torque is producing a negative torque. Or I should say this force is creating a negative torque. Now let's look at the next one. The next one over here is this 20 Newton force. There's its moment arm. And its moment arm is 4 meters long, so it gets a 4 meters. The force that's perpendicular to it would be this side of the triangle. That would be F perpendicular. And to find that side for my triangle, I need the adjacent side, which means the cosine. So it's 20 newtons cosine 30 degrees. And when I pull on it this way, it's going to cause the bar to rotate this way about C. You could just hold your pencil in the middle and jerk on each end and see which way the force would cause it to rotate. You jerk on this end, it's going to cause it to rotate counterclockwise, and we said that was going to be counted as a plus. So the sum of the torque about C, we just punch all that in. We've got 2 times 15 times the sine of 25, and then we add 4 times 20 times the cosine of 30. When we do all that, we get 56.6 Newton meters. And that's the units of torque. Do not put joules. Not a joule. A joule is a unit of a scalar quantity of work or energy. This is a vector quantity, and we leave the Newton meters alone to indicate that it's a torque. Both of those can exist in the same problem, so we do not want to give them the same type of unit. I know they're both Newton meters in a way, but we call the one joule if it's an energy and a scalar. We call the other, when it's a vector torque, a Newton meter. Now let's got the same forces, but if we change where we calculate the axis about, for instance, we're going to calculate about point P, we can see that we will get a different value for the numerical part of the torque, and we can find that even some of these forces which cause it to do, for instance, counterclockwise, like this one, if you pin it here and you pull, will cause it now to be going not clockwise, but counterclockwise. So it changes its direction of torque. Torque is all important about which axis you're talking about. So let's go ahead and do this problem here. For point P, whoops, drew my torque the wrong way. We start with the first force, which is the 10 newtons. The 10 newtons now is 4 meters, and all of it is perpendicular. So it's 10 newtons times 4 meters, and it's causing it to go in the clockwise direction, which is negative. So 4 meters times 10 newtons. So minus 10 newtons, 4 meters. The second force here is this 15 newtons. Again, we need the sine function to find out how much of it's perpendicular, and its distance to this point P is this 2 meters. So it's 2 meters, 15 newtons, sine of 25. So 2 meters, 15 newtons, sine 25 degrees. Need to figure out if that's plus or minus. It's going to cause this thing to rotate this away, which is plus, so it gets a plus sign. And then we've got another plus, and this time the distance between point P and this force is a total of 8 meters times 20 newtons times the cosine of 30. So 8 meters, 20 newtons, cosine of, and what did I say, 30 degrees? Yes, 30 degrees. So the sum of the torques along P, punch that in the calculator, minus 40 plus 30 times sine of 25 plus 160 times cosine of 30, and I get 111.2. Newton meters, or about 111, I guess, to 3 sig figs. So a different number. Torque always depends upon the axis. One last thing about this particular example. While generally you have a problem and you've pinned it, the concept of torque doesn't even require the object to actually rotate. You could choose any point you want in space. You could choose to compute a torque about a point here. Call that point B. In which case now you'd be looking at these being your moment arm. And it's for things like that where this is going to be a problem that it's easier often to think about how much of the distance is perpendicular, since it's easy for me to see the 10 Newton force here. So if I know this distance, then it's this distance times 10 newtons in a negative direction for calculating the torque. And over here, likewise, this would be like that. So it would be easier to calculate this part for any force if there was a force over here. For here, I can consider myself be this distance. And now this part is the part of the force perpendicular to this length. So you can see that the angles and things change. So it's usually best to think about it as force and a perpendicular distance, or distance and a perpendicular force. And the book spends quite a bit of time talking about that. Torque is the rotational analog of force, in that is the cause of angular acceleration, just like force is the cause of regular acceleration, and the change in angular momentum, which we'll get to in a little while. Another important thing is sometimes you have pulleys. When a string is wrapped around the pulley, the string will always, don't know why I have that, come off tangent to the pulley, i.e. perpendicular to the radius of the pulley. Thus the torque is always the tension times the distance. I like to say that that's Teddy Roosevelt. TR, famous initials of the president. Probably misspelled his name. So, for instance, as an example of that, here's a compound pulley in which this pulley here had a radius of 2 meters, and then there was a radius out here of 4 meters. And they give you this angle, but this distance and that of that radius and this tension are perpendicular. So if I'm calculating the torques for this problem, about this axis there, the torques about the center would be equal to 12 newtons times 4 meters. They're perpendicular, so it's just tension times radius, and this is causing it to rotate this away, which is plus. And this one here is 10 newtons times 2 meters, and it is also perpendicular, but it's going in the opposite direction. So 4 times 12 is 48 minus 20. The sum of the torques would be 28 newtons. The reason that they're always perpendicular is that if you try to pick this up and move it up like this, say up to here, this string would unwrap and move it back to a new point, a point where it would be perpendicular. It always comes off perpendicular to the rim. Now you can grab it with your fingers and hold it somewhere and make it not, but if it's just a rope, as in pulley problems that we had, they will always come off perpendicular, and the torque will always be equal to tension times distance. TR, Teddy Roosevelt. And that finishes our discussion of torque.